Welcome back. Now we are going to have second talk on day 2 by Dr. Manikarthik, ARCA Hyderabad, on recent research progress in supercapacitor technology and its potential applications. It's my privilege to introduce our speaker. Dr. Manikarthik is currently working as a senior scientist in Center for Nanomaterials, International Advanced Research Center for Powder Metallurgy and New Materials, popularly named as ARCA Hyderabad. Yeah. He also worked in different organizations located in South Korea, Taiwan, Italy, and Spain. He has received several research fellowships from University of Torino, Italy, National Science Council, Taiwan, UGC, India. Indian Embassy in South Korea selected him as one of the best Indian scientists for scientific interaction with the late Honorable Dr. APJ Abdul Kalam, former President of India, during President visit at Seoul, South Korea. He has received the award Best Scientist in Supercapacitors 2019, awarded by RULA, powered by World Scientific Council and United Medical Council. His research areas of specialization include material science, nanotechnology, porous carbon materials, catalysis, photocatalysis, fine chemical synthesis, air quality management and pollution control, solar energy harvesting, energy conservation and storage, batteries, and supercapacitors. His papers are frequently cited and also appeared on the cover page of the journals. He has also served as guest editor for Materials Focus, Journal of American Scientific Publishers. He has delivered several invited talks and presented his research papers in several national and international conferences. Dr. Manikarthik, he got 2 patents are granted and 7 patents are published. He published in more than 50 journals in national and international journals. Now I welcome Dr. Manikarthik to present.
Thank you very much, Dr. Srinivas, for your very warm welcome and kind introduction. My voice is audible?
Yes, sir, it is audible.
First of all, thank you very much for you to bring me to sharing our current activities, because currently I am working in supercapacitor and batteries for the application for energy sectors. So I would like to thank your organizations and GITA University for the nice opportunity for sharing our knowledge to the interested people who are working in the energy sectors audience. First of all, this energy sectors is really a very interesting field. That's India, we need energy. So a lot of laboratories and industries are come forward to develop the energy storage devices, and for particularly in India now focusing on electrical vehicles application, EV sectors. I think everyone knows the field are very booming. We need a future is electric. So if you want electric vehicles, generally we need to have some storage devices and storage materials. That is, it should be indigenous development within country. That's the reason a lot of R&D is actively going on in this field to develop the different sectors, different type of materials. The materials mainly focus on the cost effective and long durability, and it should have the high performance and safety. So these are all the very key factors for the commercialization perspective. So that's why RCA we are working actively involved in this development of materials, and we need to work for we should first identify what is the industrial needs, what industry is expecting from us. That's a very key point. Then only you can develop the technology and transfer the technology. That's a very key point. But most of the academic sectors, people are working different materials. But this forum is one of the unique forum to merge the people from academic as well as the industry. That's why I just now talked to Dr. Srinivas. He brought the people from HBL, that is a very known battery limited in Hyderabad. So from industry. So also from Anna University, Bitsblani, other is academic center. Like RCI, we are in between academic. We are not completely doing academic work. We are not doing completely industry, but we are developing the technology to the transfer the technology to the industry. But we are also having the PhD students. The hosts are really closely associated with their registered PhD in neighbor our IIT Hyderabad or IIT Chennai or IIT, whatever the IITs available in our MOU with the RCI. So they registered IIT PhD in IITs, and they are from there one supervisor is belongs to IIT supervisor. So we are also working on the academic and basic research. So we are like working with closely associated with the basic as well as the closely associated with the industry. So this very short introduction, I would like to start my today topic, the recent research progress in supercapacitor technology, and what is the potential application in various fields. People are working in supercapacitor, they know what are the applications, but some limited applications, generally supercapacitor having the wide range of applications. That's the main talk we are going to, I am going to focus in this particular forum. So just I would like to introduce our center. I think some people knows that International Advanced Research Center for Powder Metal Engineering Materials. It is the Autonomous Institute of Department of Science and Technology, Government of India. It is located in Telangana state. It's known as Hyderabad, near to airport. This is our center. Mainly, our thrust area we are working. It's a powder metallurgical institute starting from. Then slowly it's converted into, depends on the need of the nation. For example, development of nanomaterials for the water treatment, the energy sectors, and the solar field, renewable energy. And of course, now additive manufacturing is very important sectors for India, additive manufacturers. So this and all our main thrust area in RCI, particularly surface engineering, ceramics, laser processing, alternative energy, nanomaterials, automotive energy materials. So I am basically material scientist. I am working in nanomaterials with different nanomaterial development for mainly supercapacitor and battery and other sectors applications. So this is the main area of interest in RCI. So what is our, as I said, we are also working closely associated with the academic from IITs. Students are coming from IITs. We are working with them, and also we are collaborating with the industry. We are doing some industry-oriented program, major activities we are doing. So our main motivation is the technology development, technology demonstration, and technology transfer to the Indian industry. From this perspective, we are working on that, and already in RCI, we already successfully developed more than 40 technology transfer, more than 150 technology advisor, technology documentations, and technology interested with the collaborations with the industries. But 40 technology already successfully transferred with the different type of field and different field and different type of materials. For example, high strength steel, nano powders, fibers, composites, powder metallurgy, varistors, solar hydrogen energy, antimicrobial and self-cleaning textiles, two-dimensional material, lithium-ion batteries and supercapacitor, aerosols for insulation applications. We can develop the product level, and some of the products already transfer the technology, and it is available in commercialization. For example, nanomaterials for antibacterial and self-cleaning textiles, RCI is successfully transferred the technology to the Resil. The Resil is the Bangalore-based company. They already have the textiles which have our technology, nano silver and TiO2 microsphere, that is called a TiO2 nano silver based photocatalyst for they can coated on this textiles. It is act as an antimicrobial, antibacterial, self-cleaning textiles. It is already successfully demonstrated, and it is already commercialized. Because of that, our associate director and the RCA, they are already received the award from ex-president of India. And also we are working, large quantity of the silica aerosol flexible sheets for thermal insulation and other products for different type of applications. Now currently you can see we are working on the batteries and supercapacitor for the energy storage device. That is the key technology. Now currently we are working on that, because now as per the National Electric Mobility Mission Plan, vision is to develop the electrical vehicles. That is the future is electric. That's why we are most of the industry are also interested to take this technology. So this is our my colleagues headed by Dr. Katana Singh Rao. He is the Associate Director of RCI, and Dr. Or Vijay is a team leader headed in Nano Center. This is our students and our research colleagues in Center for Nanomaterials from RCI. So today topic, as per the faculty development program, in this aspects, I think all several speakers already yesterday spoke about the energy storage, particularly batteries. And the energy storage technology, particularly this faculty program on energy storage. So energy storage technology, you can see the particularly electrical energy storage technology. We see the electrical, we can see the electrical energy storage, and the mechanical energy storage, thermal energy storage, chemical energy storage. So there is a different type of energy storage technologies available. And the electrical, of course, supercapacitor, superconductive magnetic coil and all, and mechanical pumped hydropower and compressed air energy storage system, flywheels, and the heat into convert into electrical, that is called thermoelectric material, thermoelectric energy storage. Chemical energy storage, the chemical energy is converted into electrical energy, that is lithium-ion battery, lead acid battery, or high temperature batteries, what are batteries applications. So if you see the energy storage, there is a short term, medium term, long term, because depends on the energy needs, depends on the application. They are classified into short term, medium term, and long term. So the basic question: why we need a electrical energy system and storage devices? Why? What is the major requirement of energy storage devices, and why we need these energy storage devices? That's a fundamental question. We see the mechanical energy storage, chemical energy storage, as I explained that previously, lies electrochemical and electric. So now we are talking about a little bit. I am mostly supercapacitor is the electrostatic. If there is no chemical reaction, I will explain in following slides. It's electrostatic, electrical energy storage device. But electrochemical is a chemical, but that's why we are using fuel cells, batteries, solar cells. They're having involved in the chemical energy converted to electrical energy. I think you know the mechanical and other chemical, hydrogen is the fuels, hydrogen energy. So these are the major important energy storage technology available in all over the world. But India now focusing on the different technologies. But this particular talk, I'm going to talk about the supercapacitor, that is electrostatic storage device. So as you ask the very fundamental question, why we need store the energy? So you see everyone knows that the power generation from the from the coal power plant, because of the coal power plant we are producing several years we are only the power generation from coal. Then slowly India adopted that PV panel is also renewable energy technology to generate the electricity. So renewable is very important because renewable there is no pollution free. So that's the reason people are converted into renewable. But renewable is not sufficient to provide how much we need, because that's why the energy storage is important. You see there is a power generation, there is a grid, whatever the power generated from the power generation units, then transmission and distribution power to the whatever the industry or our commercialization, and end is consumer use. So these are the power generation, there is a transmission grids, and finally it goes the end users, that is the consumers, whatever the industries or our domestic purpose, because we need electricity for our normal life. So in this case, one side is production. Suppose if we have overproduction, that whatever the production electricity is waste. Another hand, if you see the demand, suppose if the less amount of electricity produced from any power generation sources, we don't have insufficiency of the power generation. That also a problem, because how you can demand is more, for your generation is less. How to you can tackle the generation? That is reason the energy storage is required, because whenever the overproduction is there, the excess energy is stored in the different technology. That's why I already explained. The battery technology, lithium-ion batteries is commercialization maybe last 20 years. But you see the our lead acid battery more than 50 years, 60 years. Now currently most of the people are using our lead acid battery. But lithium is now slowly going to replace. That's electrical vehicles, EV. Mainly we are going to focus on lithium. Also redox flow battery and sodium sulfur, sodium ion batteries, then next generation batteries are coming. So this is all are the energy storage devices. So here main point is why we need energy storage device, because whenever the overproduction is there, the excess energy can be stored in the devices. Whenever the demand is there, the stored energy can be supplied to match the demand. So that's the reason we have energy storage devices in large, because energy storage devices, if you see we can store the energy in watt level or megawatt or kilowatt, and you can go for the terawatt. So like different type of the units, then you have the mega, you can see the watt from the, you can go for the gigawatt or megawatt, a large quantity. That's the reason we can match. So we need the energy storage devices in order to match the demand whenever the energy needed. That's the reason we need to work for the energy storage. So if you see the power generation management, another thing, the power generation management is really very big topic, and people are now, you see, solar and wind energy, as I said, is a renewable energy. It's also producing the electricity. But what is the problem? Solar and it depends on the weather forecast. Because if you have this cloudy period, your solar generation is fluctuating. The same hand is wind power generation. It depends on the wind velocity. Your wind power is producing is less, the fluctuating powers. So we need some of the, some device constant power supply to the grid match, because grid should have the constant levelized stabilized power wave we need. Suppose if the fluctuation, then is a problem for the power generation management. For that, solar power and wind power, even though it's a fluctuating, then there is a unit we call the battery, that is the energy storage, electrical energy storage devices. Then we store the energy from this solar as well as the wind. Then we can provide the constant power output power supply. That's the reason this is the power generation management is very important. That battery is one of the key factors involving in that. As I said, the power plant is, we have, anyway, the pollution is coming majorly from power plant and also some of the mobility activities. So pollution is very important because, because of the pollution control is very important, because pollution is creating a lot of problems for the human being, not only human being, ecosystems and environmental problems. So we need to reduce the pollution. That is very mandate for every researchers in, what are they doing the environmental pollution control board. And you see the India, we are having annually 8.3 million people are killed due to the pollution. You can see that because of the last 1 year COVID situation, our India, we reduced, you can see a lot of environmental, Delhi completely reduced the pollution because of this COVID, because there is no transportation. So pollution is really controlled because so now we understand that pollution is majorly created, transportation is really created a lot of pollutions in our nation. That's very prove that this COVID is 1 year lockdown period. Lot of pollution reduced. You can see all the magazines and the papers are really highlighting this. This is the measure. And also industry, some of the industries not completely run because of the COVID this situation. So some of the industries are shut down. So because of that also pollution is reduced. So overall, you see the India is the now highest number of people died because of the pollution. It is there is a survey. You can see the global and health pollution. So in order to, we need to reduce the pollution. That's why the National Electric Mobility Plan is the national oriented program. So now I am coming to the topic, what we are doing. So the National Electrical Mobility Plan is one of the mission is to reduce the pollution, because we need to make the India is pollution free country. That's a major activities. That is, we need to have any program, any research activities, the government is initiated, then that is implemented in project manner, then that is funded by different organizations, then it is implemented. That is the way of, everyone knows that. So government of India launched the National Electric Mobility Mission Plan in 2020. That is the 2013 is launched, but anyway, the program is still running. What is the ambitious target to achieve 6 to 7 million units of new hybrid and electrical vehicles? So expected save is 9,500 million liters of crude oil. It's equal to 62,000 crores saving. This is just for some value that predicting the expected value. So this main impact is, if you all cars are electrified, the major mitigate adverse environmental impact from road transport. That is the clear vision. We can reduce the air pollution because of that. Because we know that the pollution, reason for the shift to clean mobility, the pollution is one of the major issue, because now India, you see the 10, 20 years before, how many cars are we used in our cities, in our even village. You can compare some small village. You can see how many cars are in the village. Now you see how much into in the expansion. You know, because of our economy, India is economically grown and highly populated country. So our economic status also growing. So the number of cars every year is increasing. So if number of cars every year is increasing, of course, obviously we can create a lot of pollutions. So that's the reason, you know, 15th, you can see the 15th of the 20 most polluted cities in the world are from India. It is the article in Hindu. You can see that India is like, this is very worst situation. But if you see the pollution, industry, of course, is a major contribution. You can see the left-hand side. Source of emission pollutions, not only transportation, in the industry also polluting, particularly our coal-based thermal power plant is polluting a lot. People on it. Then that's why we are also choosing the renewable energy, particularly photovoltaic and wind energy on the other renewable sources. If you see the industry sectors, 32% of pollution is coming from industry, of course, but transportation is 27. Even though transportation less than the industry, but industry is particular place is a stationary pollutant created. But if you see the transportation, it is a mobile. So you can the pollution is created not in one place. It's really spreaded all over the cities, all over the villages, wherever the cost transportation is very heavy. Traffic where is heavy, the pollution is particularly that area is more pollution. So transportation is very dangerous because it's completely spreading the pollutions all over the cities and the countries. That's the reason people are now working on, you know, the future is electric. So we need to work on the electric energy storage devices in order to run our electric mobility. That's the major thing. So that's there is a big question is 100% electric vehicles mobility by 2032. Is India really prepared for it? That's the questions for every researchers who are working in this field. 2032 still time is there, but still people are we are really working hard. And if you see the 5 years before that battery and other technology in India compare than now, we are really advanced and people are working lot of consortium made and people are really working for that. So this is the India also you know putting the pressure on all the research organizations, and we need to work for the, you know, for the electric vehicle mobility in India. That's the deadline is 2030. Is it possible? So if you see the any mission is there, it's according to the nation initiative program. Of course, the Niti Aayog, some people I don't know, people are working in this really government organizations and really associate the that Department of Science and Technology or Niti Aayog, they know this familiar. I'm telling people are not familiar in this field. I just explained what is Niti Aayog is a National Institute of Transforming India. It's a government of India. It's a policy maker organization that is a consortium with the government of India, Minister of Power, Department of Heavy Industry, and the Minister of Urban Development and the Minister of Road and Transport. So these are the consortium made. Every department having any unique feature. You know, Ministry of Power is power management, power supply. So in this way, grid connections, how to charging station establishment. Road means if you have the electrical vehicles, how we can the charging station implement, where is the charging station is located, and road transportation, any particular station we need to create. That is the particular heavy industries, and the Ministry of Urban Development, how to develop the where we need to put the charging station and all. So like every department, Ministry of Road Transport, of how we are, for example, now I will show some of the slides we are having. So for example, already in Telangana government put the 40 electrical vehicles in the airport to city. That's some of the program is because of the Niti Aayog is funded in National Electrical Mobility Mission Plan. So there is organizations from that they get fund, then they already implemented. So like that, so Niti Aayog is a policy maker. So this is controlling all the organizations. The main this one. That's why the mission. If India 2032 is really going to be electrified, that's why these organizations are really working on that. Then this is also DST, Department of Science and Technology, from our other organizations also working on that. Then the funding is coming to develop the very good technology. So if you see what is the big barrier of EV adaptation in India, the best way to grow electric manufacturing in India, this is just survey is having. So here, what is the big barrier means the vehicle battery prices, because we don't have any very big battery manufacturer in India. That's we are always depends on particularly China, but other countries also with the batteries imported. And you see these Because of the vehicle battery prices is really 45% of the whole core, if you see the car price. So battery is very big contribution in this price. EV charging infrastructure, we don't have very big infrastructure facilities. The lack of vehicle models and the lack of policy supports and the consumer, of course, education. So why we need to go for the electrical vehicles? And because if people are really expensive, they need to think now IC engine is very cheap. I can fill the petrol wherever I can. But if you have, I don't have any charging station, how I can shift the electrical vehicle? That is a very, that we need some education. Why we need to do and how we do. That's some consumer education. That's a very minor percentage. You can see that. Then what is the best way? So consumer end purchase subsidies. If you give some subsidies government, then people are generally moved to the IC into our EV sectors. Promoting domestic battery manufacturers, because if you have the battery, a lot of battery manufacturers within country, so you can produce productivity, you can increase the productivity, and if you increase the productivity, you can give the very cheap price for the consumer use. So investment is public charging infrastructure. Of course, suppose if I have the every petrol pump charging station, people definitely move to IC engine to battery, because we have charging station every 50 kilometers or every 20 kilometers. You have the charging station. It's very easy to see. If there is something, people are like, this is possible. If India, all the organizations, and if we combine, it is possible, because we should not compare directly America, because America or other Western countries is totally different infrastructure and advancement level. But India, you know that. But you should think about 40 years before India, now current India. That's our comparison. We should compare it within hours. 40 years before, now what we are. We should not compare with the developed countries like US, UK, or other Western countries. Now we should, think. Then we need to go forward. Investment public charging infrastructure, limiting a license plate registration, petrol and diesel. Suppose if you put the registration of the petrol diesel engine, if you more price of the tax and all, definitely people are moved to EV. So this and all the government policy. So mandate target for the automakers. So there is the automakers come forward to make very cheap car. Then automatically, if you go for the EV. So challenges and faced by electrical vehicles, you see the Tesla is the now number one. Everyone knows Tesla. The Elon Musk is a really key player in the electrical vehicle sectors, electrical manufacturer, because they are also struggling, but they are now going to be 2021, 2022. They are going to release very fast charging cars, and one charge they can go for 600, 700 kilometers. They are focusing now. Also, they are focusing going to work on solid battery. That is solid electrolytes, solid state batteries. That is going for their 1,000 kilometers one charge. That is a really excellent. But anyway, this is going on in this on the way from Tesla. But what is the problem? Still current existing Tesla is like 200, 300 miles. So Tesla still they are improving. It's a little bit old slide. So, but still mileage is very important. And another thing, battery hours, because previously the battery is charging by 4 to 6 hours. But now that's the Tesla is going to focus on high speed charging. Within 15 minutes, you can charge your car, but your car can drive above 500 kilometers or 600 kilometers. That's the, and then the people are really interested in US, but not in India. India, we go for, first we need to develop a lot of things. That's one of the slides I'm going to focus. So money is very important, because if you see the IC engine cars and if you see the battery engine, that the cost is comparison always the people mentality. So if you have the at least comparable, if the cost, then people go for, you can see there. But most of the cost is coming from the battery. So battery pack is high cost. That's the reason electric vehicles also cost. So we need to reduce the battery cost, then automatically your electrical cost will reduce. Then people will have. Other thing, battery pack, volumetric pack. How? Because your car is very limited space. So you need to accommodate your space of the batteries should be within your accommodation place in the car. Another very important is lack of infrastructure facilities, because charging station is very important for this one. So electric vehicle industry in India, you can see still we have a lot of problems. I explained this, but still there is a lot of people are really company. For example, Mahindra, Tata, and a lot of four-wheelers and hybrid vehicles and plug-in hybrids and motorcycles, scooters and bicycles. Generally, a lot of companies come forward and are developing these what are the vehicles, different sectors. You can see just I give the brief introduction of this. 2001, if you see the Mahindra Reva you can see the 20 years before is developed. Now we are in 2020, 2021, 2020 is finished. So you can see the even several Mahindra and Tata and Toyota, all our people are really developing the different cars and different battery mechanisms and things. But see, still it's not a that much commercialization point of view. It's not that much interested in the people. But that's the reason I tell you some of the reason. Here you can see the bus actually really, I can tell the bus is really success story because some of the places are really bus successfully implemented, but is particularly Telangana. If you see the, you can maybe some people are seeing that the electric bus from the city to airport to city. That is already for, there is an aim is 100 buses, but now already 40 buses is running. So that is a success story because point to point service, there is no problem for the charging station because they know the kilometer point to point, how much, then they can charge that passenger will get down, they have some rest, then you can charge again, go for. So the very short distances for the electric vehicle, there is no problem. Mainly for the charging infrastructure is not available everywhere. So anyway, I said that India is really 2001 from 20 years before really developed the different sectors, but there is a lot of barriers because government policy. Another very important is if you use electrical vehicles, because we have service station, then there is a due to the poor battery quality and lack of services and the maintenance centers is not available compared than the IC engines. That's the people are really worried where we suppose if you have any problem in the electric vehicles, where we need to go and repair. That's a problem. That's the reason some of the business has come down. Even you can see that the peak period industry went to 1,10,000 electrical two-wheelers and sales per year. So it's a really huge number. If you see the population of India, but this is nothing. But if you see the real total picture, is really huge. See that's the reason. Even there is a lot of, then they give the subsidy. The subsidy is not properly given. Then if you see the petrol diesel price suddenly is decreased, then our comparison, if you see the our IC engines also comparison 10 years before, now the car is very cheap price their production, and even you can get for the 4 lakh 5 lakh rupees, you can get the very nice car. That's the reason also petrol price is come, production rate come, then this is a competition. EV and IC engine is the now the questionable. That's the reason 2015 the FAME, the fast adaptation mobility electric mobility plan, is initiated by the National Electric Mobility Mission Plan. Is the government of India. That's they make the Niti Aayog with some organization. Then they want to promote this EV into the Indian sector. In the first Indian car, as I said, Mahindra Reva is released in even 2001. Then it's really implemented in 2010 production level. And there is a two different chemistry: lithium-ion batteries, lithium-ion lead acid battery. Of course, you know the lead acid battery everywhere in most of the our UPS and most of the all the cars engine startup and also electrical two-wheelers. Everything we are using lead acid battery. So lead acid battery, the market leader Amar Raja in one of the largest production of lead acid battery in India. You can see the lithium-ion batteries now. The cost is lead acid is less, but the lithium-ion, but you can see the energy density is 3 times lithium-ion batteries higher than these, so we can increase the kilometer. So you can see the Mahindra Reva developing both batteries. And as I said, electric bus in India 2016. Really, the circuit is first Ashok Leyland introduced in 2016. That is inaugurated by our Honorable Prime Minister. You see, after that, Bangalore, Delhi, and Manali and other states, slowly the electrical buses implemented, particularly for the point-to-point services. This is a pure electric. So now this is a success story. If you see the Tirupati Tirumala from the hills to top to hill, then there is a service is there. I think several people they know maybe traveled or they seen in the newspapers. You can see that here actually in Telangana TSRTC, it's I said the number of electrical buses is now 40. So it's one charge, 100 times 5 hours. The operation per charge is 300 kilometers per charge you go. So this is already as per the FAME initiation program. It's already implemented in Hyderabad. Then airport to city, city to airport. This is 40 buses successfully running. So as I said, this is the point-to-point service. Electrical mobility is not an issue. This is a success story. Then also you see the that's why industry is come forward to put some infrastructures or development that it is useful for our nation. So that's a Ola. Ola is a very one of the commercial transport sectors. Ola and Uber. So Ola partners India with collaborate with the Indian Oil Corporation to launch the several charging station in Nagpur. You can see this is So that is the government of India has the ambitious plan to complete the conventional electrical vehicles by 2030. All the leading manufacturers like Hyundai, Tata, Mahindra were come up with their versions of electrical vehicles. Then yet I think this is the first we can also having the electric bike, scooters, buses, or already launched by reputed brands like Ashok Leyland, Hero, Rovad, and Tata Motors. So they are also invest in the charging infrastructure. Then this is very easy for the commercialization. This is one thing, because all the people main question is we need to don't want to wait for the charging up to 5 hours, 6 hours. We don't have patient and all. So this is the some of the some small entrepreneurs, they come forward. This is called sun mobility battery swapping technology. Swapping means you can say this. I think this is already implemented in Western countries. So you can just put your cards and you can take the battery, already charged battery. Then you can put inside your particularly auto, for example. Then if you put inside, then you are uncharged battery, you can put it there. So this is very real thing. But anyway, they need to create some network wherever, because this is only one place. They are going to now focus on very metropolitan cities, but it's one place is not very big commercialization. So, but this is a very good initiative. This small entrepreneurs, they really did well, and this is a sun mobility. I think this is called swapping technology. Not already charged battery, you can take and you can put in the car. Then you can you're not like filling the petrol. It's like only a few minutes you take. Then how your petrol you are waiting in the queue, like that we can charge and I can put. This is one of the technology. So if you see the electrical vehicle sales in India, commercial point of view, you can see that the major is the cargo. Yes, because cargo is what is the success story is cargo is the point-to-point service. So also it's not necessary to go very fast. It can go very slowly. So you can go deliver like milk products and medicines products and other door to deliver. For example, now we have Heritage or any supermarket. Then you can boost to stores to other things, transportation. Now currently using the autos or IC engines. So it's creating a lot of pollution. This also a lot of people are now converting, particularly inside the campuses and for example, medical hospitals and all. They are now come forward to take the e-autos and the e-cargo particularly. And other thing, two-wheelers is also success story. You can see the 2017 compared than it's almost double times of the selling rate of the electrical vehicles. So it means people are getting aware, and that movement of vehicle is every year increasing. So electric auto rickshaws, this is also we are working electric auto rickshaws because we are buying already electric auto to modify our batteries, and we need to increase the efficiency of this. So we are working. But here, what is the electric auto is also very important because is auto, all the metropolitan cities, and really one of the major polluting creators from auto. You know that because in Chennai, Hyderabad, and very polluted, highly polluted because of a lot of transportation we need. And India is the poor country, so it's not possible everyone go by car. So auto is one of the major transportation in India. But that is if it's possible to electrify it, then it's really we are. Partially we can reduce the pollution. That's the reason people are really in Hyderabad. You can see a lot of companies in Hyderabad itself. There is a lot of companies developing the e-rickshaws. We are also working e-ride, the electrical vehicles. We already purchased from the e-ride, and we are working on that for the electrical auto for our purpose. India largest EV charging station. You can see from this 300 electric three-wheelers you can charge at a time. This is in Dwarka, New Delhi. So like such kind of activities, it's every city is implemented. Then the charging infrastructure is possible. Then we can really push all the electro people are converted into for the electric vehicles. So this is the things. Then anyway, there is a government point of view. Mr. Narendra Modi, our Honorable Prime Minister, also distributed more than 5,000 electric rickshaws in different programs. For example, Ola is the main partners, they are involved in that. So just I am giving overview of the introduction because I think this is some audience generally they are working on the basics levels, but they should know what are the real scenario pictures. I hope this may give overall pictures in electrical sectors in India, and why we are facing. I told several problems are there, but why we are not that much fast compared to others. The main issue is indigenous development. So if you see any development, we should have the indigenous development. That is Make in India initiatives. That's a very simple concept. Say this that's why I also told to my students, if you cook yourself in home, it's very cheap compared than if you go and eat at hotels. So like that, if you see indigenous development Make in India initiative, the Prime Minister Narendra Modi launched the Make in India initiative, that is called India should be the global manufacturing hub by encouraging both multinational as well as domestic companies to manufacture the product within the country. If you have the within the country capacity, of course you can reduce the drastically your cost of products, and it's easy to implement in the your our societal needs. That's the reason DST, Department of Science and Technology, we are creating the program Make in India initiative. Then there is a lot of different sectors, mainly energy sectors and additive manufacturers and other things also involved. The DST Technology Research Center's TRC program is created by DST 5 years before. Then is funded 100 crores to everyone. That is ARC International Advanced Research Center for Government, where we are also involved. We are main activities in this program, that is indigenous technology developers to the industry. ARCA mainly working on the energy sectors, particularly for the batteries and supercapacitors and energy efficiency. We are also working in fuel cells, electrical hybrid vehicles, solar energy, the concentrated solar power, as well as photovoltaic. So these are the main activities from this program we are carried out. And here actually I already discussed with Dr. Srinivas regarding this collaboration, particularly this talk. You see the institute industry interactions is very important, because it should bridge the gap. You can see from the India, the investment and the technology readiness level. This technology readiness level is created by NASA in very long back in 1978. But in most of the, particularly people who are very closely associated with the foreign countries, and people are really working in industries and particularly in government organizations, they only know technology readiness. In several people in India, I am sure they don't know what is technology readiness level. So technology readiness level, suppose if anybody tell technology, I am the technology readiness level 8 or 9, we can judge where the technology readiness, whether these people really close to market level or in basic level or which level they are. That's this you can see, this is a technology readiness level. People can see the internet, you can see what is the 1, 2, 3. It's a like basic research. So most of the 90% in Indian organizations, Indian institutions, everything working in basic research. We are in basic very strong. I agree. Indian Institute of Technology, National Institute of Technology, we have all a lot of institutions, and Indian Institute of Science, everyone working, we are very strongly working basic. We develop so many materials, but all the materials in lab level. So because one reason is investment is very less. So we are not able to get this product into the commercialization. That's the major problem. And because of lack of knowledge, some people that are really working very good, they have very good material, but they don't know how to approach the industry. Because this kind of forums, the industrial people come forward, they are presenting their works, and also some of the researchers, they are presenting their works. That's mutual collaborations happen. So then only we can bridge the gap. For example, if you see the 1 to 4 level, it's a basic level. Even though I can prepare 1 gram, then we can prepare up to 100 grams maximum. That's it. Up to 100 grams is not going to be a scalable program. And also your properties in 1 gram, if you make the 100 grams, is totally different. We have some optimization process, and 100 grams to in kg level, then kg level to several kg level. That is a challenge. That is industry sectors. So it's not possible. Everything is academic is not possible, because you have infrastructure, you have other activities, and there is a lot of hurdles are there. So it's not possible to immediately work on kg level to transfer this out. So that's why bridging the gap. So there only we have coming for the indigenous low cost technology. So that's mainly what we are working in this discipline. We are mainly focusing on whatever the technology we are working, we should focus on above level 4. It means already in gram level is a prototype, we succeed. Then how to scale up this material, and this scalable material, how to contact with industry. Then the industry, how is scalable within country with using our own infrastructure. Then come to the how to convert into the commercial usage. That's a very important. So if you see the industry having a lot of investments, they are doing really technology readiness level is about 8 to 9, but now commercialization. But most of the technology they are buying from abroad. All the equipments coming from outside. So but they're developing. But what we really doing indigenous, that we need to focus on. That is the main thing. The institute industry collaborations frequently happen. Then industry funded to institute, industry put the knowledge on the industry, then we can develop our very nice indigenous technology in India. So that's why EV components people, now I'm talking about battery, because I'm chemist, I can develop only batteries and battery oriented materials. But even there is, we need to make the device and the other, you see the electrical vehicles, not only battery, it's having other components. So it is electrical engineers, mechanical engineers, chemical engineers, production engineers. So everything is a mixture of, mixture of things. Then only you can run the EV. Only battery, you are not able to assemble, it's not possible to run. So these are the mixture of the components is very important in order to real application. So electric vehicle component market, you see, is a 20 now present 2025. It's a very huge billions money involved. But most of the India we are buying from China. You can see the even your mobile phone. If you see the scratch card or whatever your component, mostly coming from China. Even small bolt and nut is coming from China. This is India. The industry generally they are not mainly focused. We are. That's why the foreign people utilizing Indian population. India is a very huge populated country. So people identify we are the very big customer for them. That's the reason all the manufactured battery. Today lithium-ion batteries, all the batteries coming from China. No lithium-ion batteries is manufactured in India in large quantity. That's the reason we are focusing on. We are going to work on that to manufacture. You see, that's why I'm just put this, because now last 1 year we are COVID, we are everything by China, this including the COVID. Now we also get COVID. Very lucky now we are, the medicine is discovered. So from we can, so like that, we need to think future generation. So we need to work for the, we should have our indigenous thing, everything. So the medicine also, if we are not developing indigenous, suppose somebody stopped providing the medicine to India, then what happened? Think. So everyone, this is like not only all the sectors, doctors, engineers, everything they need to, think in this direction. So now really I'm coming to the topic. This is just overview of that, all the things. This is very important what I concern, because this is giving some brainstorming for the people. Always working the basics is very important. Then this also, what are the current activities going on in India, and this is we need to see what we need to do, develop. Then how to collaborate the industry, how to develop our always I will tell you the lab to self. So we need to lab to self means we need to product the lab products into the self. It means commercialization. The product is available into the market. That is the self. So lab to self is very important. We need to work on that. It's not a overnight journey. It's having like a lot of, it takes some several years. We need to work on, then you need to convert into the real market product. That's very important. So here, electrical energy storage, lithium-ion batteries and supercapacitor. I think the previous speaker, they already talked about lithium-ion batteries. And now we are also working, but in this topic, I am focused on supercapacitors in advancements and potential applications. Because you see, lithium-ion battery supercapacitor as an energy storage device, you know that is different sectors: elevations, mobility, stationary applications. These are the very major sectors I am telling. Mobility, we are talking about EV, because we are working in EV sector. So also stationary is important. Grid management, already explained. Some storage devices, and also the windmills. So many things. Mobility, there is different sectors, mobility sectors, and elevation sectors. So these are the major applications of the lithium-ion batteries and supercapacitors. So if you see the before, I think I'm not going to be much time in lithium-ion batteries, because lithium-ion batteries already the people export from that HBL. It's a battery limited. I think some of the overviews are given about batteries. Here, actually, we should thank these three guys, because these guys really is a pioneer in lithium-ion batteries. That's the reason they are getting Nobel Prize in Chemistry 2019. That is, Dr. Whittingham and Goodenough and Yoshino. So they are is a pioneer, and they are the godfather of lithium-ion batteries, because without them, now we are not able to use our cell phones and our phones, because they are the major contribution in lithium-ion batteries. So hats off them, because they are the initiative in lithium-ion batteries. Now we are enjoying this chemistry. So if you see the lithium-ion batteries, there is different chemistries there. Depends on the voltage window, and it depends on, as I said, if you develop, that is within the three triangles. One is the cost, another one is the performance, another one is the durability. These are the very important. But another thing, safety, because EV, because we are driving, we are using ours, because we need to put our batteries under our seat. So the batteries will be very safety. Then only we can drive comfortably. So in this case, so these are all the very important categories. The mainly cost effective, performance should be high. Another thing is durability. How long the battery will come. So in this category, you can see the different chemistries developed in the LCO based chemistry, lithium cobalt oxide, lithium manganese oxide, LFP, lithium iron phosphates, NMC, nickel, manganese and cobalt, and NCA, nickel, cobalt and aluminum, and LTO, lithium titanate. So these are all the major chemistry involved in that. You can see the different chemistry having the different potential window and a different energy density and different type of applications. So one material, one chemistry, for example, LCO, LCE, that is commercial battery available. For example, cell phones, laptops, cameras. That is a very long back discovered, and that's the reason these three guys are very important for this chemistry. But now LFP, LTO is we are also working in RCI, develop a large quantity of LFP. LTO is another sector, even though it's giving the less voltage, less energy density compared than the other. It's having the very long cyclability and very safety battery. So I'm not going to in depth in this because you can see the different material development is very important, and this based on the material property, then only we can enhance your performance. If once the performance enhanced, then only this battery can be a commercialization. So this and all the things, and I'm not going to in depth in every batteries, but just overview I am giving. Now I am coming to our topic. Is a supercapacitor. It's a we are developing materials and to the device. As I said, the technology is very important because material level in grams level is not possible to transfer the technology. So we need to make the in kilogram level. Then we make the device. Then that device is going to be a commercialization applications. So in this case, just you need to know that what is the difference between lithium ion and the supercapacitors, and what are the major applications and major difference. You can see the major difference is energy density. We can see this toy is very bulky, this lithium ion capacitor, because it's having more energy, but it's not possible to run very fast because of the very heavy. And that's just for the cartoon image, I will just explain for the beginners. If you use a small toy, it's having very less energy, but it is very fast. It can run very fast. So this is simple difference between lithium ion battery supercapacitor. Supercapacitor can deliver very high power density. Lithium can provide very high energy density. You can see the power and the energy. The power is the consumption of energy in unit time is called power. We can see the specific energy is very high for batteries, but less power. Ultra capacitor is, or so-called supercapacitor, is having more power but less energy. So this is the vice versa, opposite behavior, because battery is giving high energy but less power. Supercapacitor is giving high power but less energy. That's why the so-called Lavon plot, you can see the supercapacitor in between capacitors and batteries. So it's having the property of high energy density compared than the capacitors, high power density compared than the battery. That's why it is in between the batteries and supercapacitors. So this is just example of this for the beginners. If you see the marathon it's called a battery. 100 meters is a supercapacitor, because marathon you should have more energy hold within you, then only you can go run for long distance. That's called marathon race, because we need to here not necessary for you need to run not fast, you need to go slow, even slow, but you need to go for a very long time. That's called a battery. But here supercapacitor is a 100-meter race. If you see the very short distance, within fraction of seconds, one person is with another person. That means you need to have very high power in order to win the race. That's the reason, very short distance, but it gives you the very high power. That's the comparison of for the beginners in this field. What is the difference, major difference between battery and supercapacitor? So as I said, RCA is really, we are working on the development of LFP LTO in large quantities in kg levels, and we filed several patents. My colleagues Dr. Anandan and Dr. Tata Narsingh Rao, and in Chennai Center, Dr. Raj Prakash, our teams, they are working really well in the development of materials and making the batteries for the, we already success 18650, 21700 and several batteries, and we already tried the two-wheelers and bicycles and as well as two-wheelers with the collaboration industry. And these are the LTO, large coated, several meters coated the foils with the anode and the cathode. Then we assemble the cells, and this is the slurry making, mixing all the, you have the complete fabrication lines is in Chennai center as well as in ERC Hyderabad center. We are making the cells for the commercial applications. Now this technology is very interesting. We are really going to implement it in the industry level. So, but this is very good. But what is the problem is raw materials. Why we need to focus on supercapacitors? So lithium-ion batteries, this is the coming years, as I said, a lot of people are working on lithium-ion, but lithium-ion is good. But where is the raw material? There is no lithium raw materials available in India, particularly. You can see the most of the lithium is coming from South Africa and North Africa, America. And if you see the Australia and China and some of the African countries, but we don't have any mines in India. That's the reason we don't have any raw material in India, so we need to depend on the others. So that is one scenario. That's now people are focusing on other chemistry. Now lithium-ion batteries, they can go for sodium and potassium-ion batteries or magnesium-ion batteries, metal-ion batteries. So that means this sodium and potassium, magnesium, we have plenty of raw materials available in India. So we can easily adopt this technology, but there is a lot of challenges in that. So lithium-ion battery technology, well known. That's why people are focusing. This immediate commercial lithium-ion battery is viable. People are working on that. But particularly India, unfortunately, we don't have any raw material. So we need to also depend on, that's a lithium. For example, lead acid battery very popular in India because we have lead chemistry. Lead chemistry, that's the reason most of the commercial application lead acid is a successful story. But what is the problem? Lead acid maximum you can go for 40 watt-hour per kilogram. Energy density is less, so we are not able to. And also charging time, very slow charging characteristics of lead acid. So it's not possible to apply everywhere. So it is a limited application. That's why people are working on the higher end battery. The battery should very fast charging. At the same time, it has the hold the high energy density. That's the reason lithium-ion batteries is a very good candidate. But in India sectors, we don't have any lithium sources. That's why we have alternative. For example, supercapacitor. We are also we need to consider for alternative. But supercapacitor also we have very big problem because it's not having the high energy density, which have only the power density. So now we are working how to improve, and we are working on the hybrid system. Suppose if you see the lithium-ion batteries or lead acid batteries, the supercapacitor, how we can economic and performance increase cost-wise, as I said, life-wise, as well as the performance-wise, how to implement it. So supercapacitor is not alone, cannot use as a energy density device, but it can use as a complementary device to support any devices wherever the power requirement is there. That's the reason supercapacitor is the, we call it new generation or next generation energy storage device. So you see the supercapacitor, it's a very simple chemistry. It's carbon-based chemistry, carbon-carbon electrode. So here generally we should not call anode and cathode, unlike batteries, because batteries, anode and cathode, we are talking about because there is a chemical reactions, oxidation and reduction. That's why we call it anode and cathode. But here, supercapacitor, there is no reactions between, there is no chemical reaction between two carbon. So we need to call always positive electrodes and negative electrodes. Carbon, active, both electrodes made up of carbon, it's a porous carbon. So this is the fundamental phenomena of electrical double layer formation, because porous carbon is coated on the current collectors. Then if you apply the potential, then you can see the, because of the polarization, the ions are separated in the two different polarity. So we have the formation of electrical double layer. This is Helmholtz electrical double layer. Because of this, electrical is electrostatically, the charge is happen in the activated porous carbon. So whenever this is charging state, when you are applying the load, then the charged state electrical current is passing through the load, then we are releasing the discharge state. So this is the method. Here what we are using, only the carbon based. So carbon is plenty of material available in India. That's the reason we are choosing this technology, and we are developing large quantity. And here only is separated by the separators. Separators should be the electrically insulator and ionically conductor, because here we are using electrolytes. So it's very simple chemistry. I will tell you this also very complicated. I will tell you when you are going for the technology level. So if we see the separators, then separated by the two porous carbon is highly high surface area. Then we are using different type of electrolytes. This electrolyte determine your voltage. Because if you say the aqueous based electrolyte, for example, KOH, sodium hydroxide, 6 molar KOH or 1 molar sulfuric acid, as the well-known electrolytes. But these electrolytes having dissolved in water, because we have water aqueous based electrolytes. What is the problem? Aqueous based electrolytes, the water electrochemical potential window is 1.23 volt. Above 1.2, water can spill, it becomes hydrogen oxygen. So that electrolyte not suitable for above, then you can have the electrolysis. So it's happening to spill the water into become the hydrogen and oxygen species. So it's not useful for as electrolyte. So the window aqueous electrolyte is limited. So we can go for maximum 1 or 1.1 volt. Another thing, if you use the non-aqueous electrolytes, then that we are using non-aqueous solvents, for example, tetraethylammonium fluoroborate, that is a TABF4, is a well-known commercial organic electrolyte salt that is dissolved in acetonitrate or propionate carbonate. That's that electrochemical window we can go up to 3.5 volt. Suppose if you use the LiPF6, lithium hexafluorophosphate, some people are using. When you go in lithium hexafluorophosphate or ionic liquids, you can go for above 3 to 4.5 volt. So this is all the electrochemical window depends on the electrochemical stability of the electrolytes which are using in these supercapacitor devices. But why we need to go for higher end? When you are going for aqueous, then there is in between. It's called neutral electrolyte. Neutral electrolyte is a sodium chloride or sodium sulfate is a neutral. There is no pH variation because if aqueous, we can go for KOH is basic electrolytes because KOH is a basic. If you go for the sulfuric acid is the acid-based electrolytes. So these both are dissolved in water. So these electrolytes, water-based electrolytes, is called aqueous-based. As I said, voltage window is limited. But even though sodium sulfate Na2SO4, it's aqueous-based, but you can go for the 1.8 volt because of that there is no pH limitation. So we can go for 1 volt, 1.8 volt, and up to 3. Then we can go for up to 4.5. Depends on the electrolyte usage because this electrolyte mainly depends on the stability window of your electrolyte, even though it is used carbon-carbon based. So if you see this carbon-carbon based, there is no, the material is, we can develop the carbon-based material. So that's the reason is it's viable in India. So if you see the electrochemical capacitor or generally people are called ultra capacitor, super capacitor, it's basically two types. One is electrical double layer EDLC capacitor or pseudo capacitor. So electrical double layer capacitor means non-Faradic, no charge transfer between the electrode and electrolytes. So it's only the electrostatic interactions of the solid electrolyte interface. It's forming the electrical double layer. So there is no redox reactions. There is no charge transfer happening between electrode and electrolytes. So it's like the interface. That is, electrode is solid, electrolyte is liquid. There is an interface that this electrode and electrolyte interface, there is ion storage. That's why we are creating the porous carbon. If you increase the porous carbon, I will explain this in formula. Increase the porous carbon because this is a capacitance depends on the surface area. If we have the more surface area, more ion Q, C equal to Q by V, then depends on the voltage and also Q by charge. How much charge is storing in the unit volume of the your electrode? Then you determine your capacitance, how much farads. If you see the pseudo capacitors, it's having the charge transfer from surface Faradic reactions. It's called react reaction. You can see the best example is some metal oxides, ruthenium oxide, titanium oxide, and manganese oxide. This also having the electrode is solid, electrolytes liquid. So electrode electrolyte interface, there is a charge transfer between the electrolyte and the electrode. So this is like pseudo behavior. It's not, there is no chemical reactions, but it's a pseudo. The only charge transfer from M1, for example, any metallic M1 plus is released the electron, then it comes M1 minus. So electron transport is happening. Because of the electron transport, there is a charge transfer mechanism. Then your circuit is happening because of the flow of electrons. So it's having the pseudo capacitor. So this is the major difference of electrical double layer and pseudo capacitor. But here, compared to the electrical double layer pseudo capacitors, you have the farads difference. For example, here you have get more farads in pseudo capacitor because of the there is a pseudo behavior. That's the reason we are having more capacitance compared than the electrical double layer, because this is only, it depends on the porosity of the carbon. So there is no chemical reaction, there is no electrostatic interaction, this charge transfer interaction. So it's having the limited. So maximum as per the state of the art, if you use the EDLC, you can go for maximum organic electrolytes. You can go for 100 or maximum 150 farads per gram. Not able to increase because already saturated. Because I will explain the carbon behavior also in following slides. If you see this one pseudo capacitor, even the people going for 600, 700 farads per gram of the active material, but based on the active material. But what is the problem is, commercially point of view, this pseudo capacitor having the very less cycle life compared than the EDLC, because there is, because of this mechanism. And another thing is the voltage window of the pseudo capacitor is less compared to the electrical double layer capacitor, because you can go for different electrolyte. I said, for example, tetraethyl ammonium tetraborate, it go for up to 3.5 volt. So we can have the E equal to of CB squared. So V squared voltage is increased double, then your energy density is higher. So your voltage window of the particular device is very high. So this is the limitation of EDLC and pseudo capacitors. Then the next generation capacitor we called lithium ion, that is a hybrid capacitors. It's nothing but, as I explained, that lithium ion battery, you can see the graphite as anode, and you can see the LIM, lithium metal oxide. For example, as I said, LiCO, LMNO, LMNC, or whatever the compound is as a cathode material. So if we see these two material is having, because of the lithium ion batteries is having the lithium ion batteries graphite, if you lower potential, that's why people are using lithium intercalation have lower potential, but here is having higher potential. Then your voltage is determined by the, as per the your full cell E cell equal to E cathode minus E anode. So we can get the full cell voltage. So this is the lithium ion batteries is happening. But super capacitor, as I said, depends on the both are carbon based chemistry. So it depends on the electrolyte. It's you determine your final voltage window. Then super capacitor, that's the reason it's giving very less energy density, but it's having, because of the very fast absorption, it's deliver very high power. But here the kinetics is controlled because of the kinetic control. Here your rate of reaction is very slow intercalation. That's the reason it's deliver very low power, but energy density is very high. So if you do one electrode from, for example, graphite from the lithium ion batteries, another electrode from activated carbon from the supercapacitor, if you combination of this, we can achieve high energy as well as the high power. So this is a hybrid sectors. So one electrodes from the lithium ion chemistry, battery behavior, another one is from the supercapacitor behavior. So if you combination of this, we can go achieve the hybrid capacitor, but this is for in between. It's giving a high energy density compared than the supercapacitor. It's giving high power density compared than the lithium ion battery. So hybrid system is very useful phenomena because we can increase the voltage window. That's a very important. As I said, voltage is very high, your energy density is very high. So this go up to 3.2 to 4.2 volt for the hybrid supercapacitor device. That is called the so-called LiC, lithium ion capacitors. So if you see the lithium ion capacitor also, as I said, this is the simple carbon based, that is EDLC capacitor. LiC, as I said, one is from battery, graphite, particularly this one. So graphite AC, even though this one, as I said, 3.2, 3.8 to 4. You can go higher voltage. But if you see the some other, because graphite having a problem, SEA layer formation. SEA means SEI layer is very big issue in the battery chemistry because solid electrolyte interface. That is, if you use the graphite, it's more layer is forming, then your voltage window is high, but lifetime is less. But if you see the LTO, lithium, so-called lithium titanate, then it's a mixture of carbon nanofibers or any carbon conductivity, because LTO, in order to increase the electrical conductivity, we can have some composite material. This LTO chemistry, we can go for less voltage, maximum we can go for 2.2 voltage, but you can have for long stability because there is no SEA layer formation, because it's a LTO lithium intercalations above 1 volt, particularly 1.55, so above 1 volt. So there is no SEA layer formation. So this combination LTO activated carbon is really giving for long cycle. So that's the reason two different next generation hybrid capacitors available. So people are doing. We are also working on that. So if you see the different EDLC, LiC, aqueous based, non-aqueous based, different type of material, this is now several review articles explaining very well about the different type of combination. What is the, so finally we should have the very good high energy density and high power density. So this combination is very important for any application, particularly EV application. We should have the high energy as well as high power. So both are very important. So this combination chemistry will work on that. You can see the non-aqueous with the other, for example, titanium carbides and all carbide-based carbons, and this is useful for the pseudo capacitor as well as LiC. You can see the LiC is having high energy density compared than the AC. So these all are different combinations. It is well known in literature. So if you see the fundamental of the electrical double layer capacitor, as I said, the capacitance is surface area divided by separation of charge distance. Here, this is the separator. As I said, separator is the ionically conductive and electrically insulator. That's why without short circuit, you can put the two our positive electrode, negative electrode. Then we can separate by insulating material. Then we put the electrolytes. Then you can see that this is the current collector. Basically, we are using carbon coated aluminum foil or aluminum foil as a current collector in both cases. If you see the electrode is coated on the current collectors, and this is the you can see the cell made. So if you see here, there is a putting the electrolyte, then there is a formation of Helmholtz layer. That's why electrical double layer. Then it is according to these. You can see the formula. Capacitance farads per gram is a Q by V. So energy density E equal to of CV square. When the capacitance is, even the capacitance is very important, but voltage is very important because V square, if you increase the higher voltage, then your energy density is very high. That's the reason we are using the organic electrolyte as compared to the aqueous electrolyte. Organic electrolyte having higher potential, total. But here, there is a lot of phenomena I will explain later. What are the things will affect your EDLC capacitors and why that we need to increase the high performance capacitor. What are the parameters? I will explain some few slides later. These are mechanisms. Already you can see the working principles is very simple because if you apply the potential, there is in YouTube very nice simulations how these are the porous electrode. Then because of the potential, you can see the apply the potential. Then because of the polarity, then ions are separated from positive ions is go to the negative terminal and negative ions go to the positive terminal. You can separate because of the you can see the porous network. It's very nice to explain in this YouTube for the simulation purpose. The beginner they go and see this this kind of videos. They can easily understand the mechanism of the supercapacitors. And you can see this. Suppose the supercapacitor, you can see the really booming lot because a lot of people are really working and to develop the different type of material. As I said, these three parameters very important: cost effective, performance, and durability. From this, there is a different type of combination metals already prepared and working very well in state of the art. You can see that the carbon is very predominantly publications in more than 20,000 or 2 lakhs publications is there in more than 2 lakhs publications is there in carbon based chemistry compared than the other things because carbon is very cheap material. They are really lot of biomass. They easily burn and they are activated in. I will following slides. I will explain what are the activations they did. Then that's the reason a lot of people are working in all over the world in carbon based material. Other also, for example, metal oxide, pseudocapacitors or waste to wealth, from waste to biomass to convert into other type of material like carbon clusters, carbon particles, composites, and all. People are working with the polymer based material. Here, the material design is very important for the supercapacitor perspective. How you are designing your material, then only that design of material is depends on your performance, final performance of your device. So here, if you see the always I'm telling the cost, performance, durability because this is a very important point for the industrialization. But if you see the energy density of CV square, so we need to increase the C as well as the V square. Then only you can your energies depends on the capacitance as well as voltage. So if you increase the capacitance, of course we need to have the specific surface area, the pore size, your material having very good electrical conductivity and additional redox capacitance. Then we can increase the capacitance. V squared, as I said, if you see the organic electrolytes, ionic liquid or asymmetric supercapacitor, then you can increase the V. So both if you increase this category, then your energy density is increased. So this is a very key parameters. People are look on that to how to increase your energy to modify your materials. You can see the left hand side, the people are specific, as I said, carbons, polymer, metal oxide. These are the several material focused, but these are the major material focused and they get very good results. You can see the lithium oxide giving 1200 farads per gram. It's very high with a different type of chemistry, lithium oxide with the carbonate, CNT or polymers in order to increase that performance. But 1200, as I said, even lithium oxide is giving very high performance, but the cost is very high and the durability is very low compared than the carbon. The carbon-based chemistry, activated carbon, maximum capacitance in aqueous based or organic based. Organic based is 100 to 150, but aqueous based is giving 200 to 300. But what is the problem? What is the major advantage of carbon is long durability because it's a EDLC mechanism, as I said, adsorption, desorption. So there is no chemical reactions and electron transport. So in this case, the carbon is life cycle is generally 1 million. So 10 lakh cycles you can go charge discharge. There is no day. So its lifetime generally 10 years. Maxwell is reporting this. Maxwell is one of the familiar, well-known company in world manufacturing a supercapacitor. I will explain some other slides. You can see that that Maxwell capacitor using the activated carbon is having 1 million cycle charge discharge. That's the reason carbon they are using. Other chemistry, Maxwell also using the pseudo capacitor released that voltage is 2.3. Maximum they are released now 350 to 400 farads per device level. So here, in this case, the cost is very important in order to choose the material to commercialization. So you can see I will giving some of the data regarding the cost versus the performance. The coconut cell activated carbon is the coconut activated carbon is the less price, giving the optimum performance. For example, 100 farads per gram. There is a Maxwell using coconut derived carbon from Kurare. It is a Japanese-based company developing the YP50 that is developed by coconut cell-based activated carbon. That is carbon only Maxwell is using. You can see the coal tar or petroleum coke derived carbon. If coal tar is very cheap, but performance very less. If is a petroleum coke is giving very good performance, but cost is expensive. Other type of graphene polymer nanocomposites also is giving the good performance but cost. So if you see the cost versus the material development, that is cost is very important for the industrialization. So in this case, that coconut cell based activated carbon is the worldwide is a commercialization purpose. Worldwide, the supercapacitor is made by coconut cell based carbon. See here, actually, I said if you see the capacitance directly proposed to surface area, that is true, but not only surface area. You can see your activated depends on your activation condition. You can go for the surface area up to maximum 2,500 square meter per gram, but there is a limitation in 1,500 to 1,700 surface area only. It's giving the very good tap density because you need to coat your material on the surface of the current collectors. So it's having the very porous, it's like spongy type structure. So it's not possible to coat on your current collector. So it's have the tap density means your material density, also it's having some certain porosity, also it should have some surface area. So these three parameters very important for in order to increase we need to consider the tap density, also performance. So in this case, YP50 is the activated carbon. It is used in Maxwell supercapacitor that is having surface area between 1,500 to 1,100. The pore volume between 0.6 to 0.7, and the pore size, there is a bimodal pore size distribution. 0.6 I will explain in following slides. 0.8 nanometer, 1. This is required, and electrode density 0.6 to 0.7. But actually goal, you can see you can see the energy environmental science journals. These people explaining that these are review articles. You can read this energy storage materials and energy environment. It's a review article. Explain that. You can see that when increasing the tap density, you can volumetric. You can store your capacitance in more volumetric manner. If you have the very less material load, your material may be giving high gravimetric, then it's not going the high volumetric. So if you have more material, then is other technology problem will come, because if you have more material is not adjusted with the current collector, it may peel off from the material. So these are the optimization parameters we need to do for the commercial purpose in order to get the very high performance supercapacitors. The other state of the art commercial level 90 to 100 farads per gram. Then it's around you will have the 0.6 to 0.7 electrode density is around the 40 to 60 or 70 farads per centimeter cubic. It will come. So if you see the surface area and pore volume, pore size is very important for the supercapacitor performance. If you see the chemical, so this how we can make the very good surface area and very good pore size. So this is depends on how you are synthesizing the parameters, synthesizing final materials. So generally, instead of the art, people are making chemical activation and physical activation for the carbon material in order to make the porosity, surface area. So generally, if any biomass or any carbon, pyrolysis is the main, is called carbonization. So you need to first make the biomass into the carbon. Then carbon is, that carbon should be very high pure carbon. There is no any other impurities. For example, any minerals are there, it will affect our performance. So 100% pure carbon can be activated by physical activation or chemical activation. So physical activation method is used. You can use the air or steam or CO2 in order to activate your carbon in certain temperature. This is well known in the literature. If you see the chemical activation, Chemical activation is using chemical, for example, KOH, sodium hydroxide, or zinc chloride, or iron chloride, or phosphoric acid. And some people are using microwave activation, but that is not industrially viable. But physical and chemical activation people are doing. In that two category, physical activation more economic. For example, physical activation, your yield is very less, but your processing, you can control the processing steps. For example, chemical activation, yield is very high, but you need to remove, after activation, you need to remove the chemicals from the activated agent. For example, KOH. KOH is very hazardous material, and also after activated, it's a porous material. The KOH or any chemicals, it is embedded inside the pores. It's not very easy to remove the chemical species from the activated carbon. So we need to plenty of water washing or neutralization in order to use the acid to neutralize the carbon in order to make the neutral carbon with the high purity carbon. It's a very challenges task for the chemical activation. Physical activation, generally already purified carbon. That's why I told you, if you make biomass converted into carbon, that carbon should be 100% purity. Then only that purity carbon, physical activation using air or steam or CO2, then you can convert to the porous carbon. Then that is useful because you can eliminate any other washing steps. So that kind of carbon economically viable. That's the reason the steam activated, and some people are using steam and CO2 both activated compound is a well commercialized sample. You can go for large quantities in the size. That's the reason Kurare is Japan company. It's making the activated carbon. They are a major supplier of Maxwell supercapacitors. So here, everyone, this chemistry is very simple, but really this chemistry is not very simple. You can see, you need to very fine tune your carbon according to the which electrode are you using. So you can see these papers are really explaining very nicely regarding the what is the correlation between the pore size as well as the ionic size of your electrode. That's very important parameter, because if you see the ionization, any material, for example, if you see the aqueous, it's having for example, KOH, aqueous base, K plus OH minus, so 2 ions. So this is we called bare ion. But if you have the water molecule, so solvation effect, so that ionic size is bigger. The bare ion size is bigger, is smaller than the ionic solvator ion size. So it's having the different type of ionic size. So these ions only enter the pores, then it's absorbed. So if, for example, tetraethyl ammonium is a tetrafluoroborate, is a copper shell electrolyte. This is a salt, it dissolves in acetonitrile. You can see the bare ion size. For example, tetraethyl ammonium is around 0.7 nanometer. BF4 is around 0.48 nanometer. Acetonitrile is around 0.8. Suppose if we have the solvation effect, it's a cation and anion, it increases size 1.3 to 1.4 nanometer. For example, is a cation. If you see the anions, it's increased to 1.2 to 1.6 nanometers. So it's having the bulk diffusion inside the pores. If the pores is very narrow mouth, these ions are not able to penetrate inside. Suppose if you have the wide end, it can really go. If you have the very wide end, it's a very computational absorption of too much. So if you see this, here another challenge is tetraethyl ammonium is different size. Here is a different size. This is the bigger size. This is a smaller size. So now that is a challenging task for the the material scientists. We need to develop the material which have the hierarchical pore structure. So it means this material should have the high surface area as well as pore size distribution. It's having the microporous as well as the mesoporous. Suppose if you have a very completely microporous, generally the definition of microporous less than 2 nanometers is under the category of microporous. If ultra microporous less than 1 nanometers, ultra microporous. Suppose your pores is very ultra microporous, less than 1 nanometer, is also a problem because it increases surface area. That's why one of the slides I showed previously, surface area 2000, 2500 is you can increase by decreasing the pore size. When you do ultra micropores, your surface area will increase. But on the other hand, your ionization, this whatever the ions is not going to penetrate into the pore. That's a problem. So same thing, your microporous pores is contributing the surface area. The mesoporous is contributing the electrolyte diffusivity in order to penetrate all the ions go to the micropore. So this combination is called hierarchical pore structure. So micro and the meso certain combination is giving enhance the performance of rate capability as well as the high performance of the supercapacitor. So this is really tricky. You need to fine tune your processing condition in order to obtain the final carbon material for the commercial application. So as I said, if you see the supercapacitor in laboratory level, is very easy because you can make some electrodes. Maybe most of the people are working. I would like to point out here, most of the people are working in 1 mg, 2 mg coating on the surface. You see the 1 mg, 2 mg in laboratory level, there is a lot of problem is come for the measuring the weight also, because your balance 1 mg weighing also, there is a lot of error in that, in the students level I am talking about. So from that 1 mg, 2 mg weighting itself, you lose very small milligram less, your error is very high. So if error is very high, whatever your calculation, final calculation is wrong. So you are misleading your material performance compared than the step. So if we increase the, for example, Maxwell's and the commercial level, we need to quote per square centimeter more than 10 mg per square centimeter. But 10 mg square centimeter active carbon is challenging task, because if we quote more than it will of quote less, you have the problem for the measuring or whatever. So this is the commercial standard. So in this case, there's a lot of things involved in that, in the commercial perspective, not lab, because most of the people, students are coming, I am cutting one gram or 1 milligrams or 2 milligrams, but we are getting really very high performance, but they are calculating in farads per gram. So they are quoting in milligram, they're converted into grams. So there is a lot of error into the measurements, also experimental conditions. So they are misleading the results finally. So my advice is always we need to do some little bit. Anyway, this is very tough, but we need to go for more material loading, and we need to go for more reality value to the state of the art. So in this case, mass loading, experimental setup, electrode thickness, electrode density, active material quantity, it's determine the specific capacitance of the particular capacitor. So if you anything mistake in mass loading, your experimental setup also having the problem, because suppose you are not properly tight, there is a ESR, then IR drop, internal resistance will drop, then electrode thickness, if you more electrode, there is a diffusivity problem, so ion diffusivity problem into the electrolyte. So electrode thickness, electrode density, yes, the tap density, very small tap density is having the low volumetric, very high tap density having the high volumetric, but you need to optimize the condition, then only we can go for very good electrodes, and you control the diffusivity. Because if you see the charge discharge profile, you can have the charge and discharge. Then we are charging, when you're discharging, you can find there is a drop, it's called IR drop. People are working in this field, they well known that IR drop. This IR is generally created by the ESR, is called equivalent series resistance, and also EDR, equivalent distributed resistance. So ESR means it's coming from equivalent series resistance. The resistance is arise from cell making, because you are coating your carbon and your and the current collector. There is the interface between the current collector as well as the carbon. It's also creating the resistance. And if you have the electrodes is very thick coated, then you have the resistance of ionic resistance, diffusion, ion diffusion resistance inside the electrode. That also will affect. So these all are when you are making the cells, because you have the carbon coated. That's why we are using the carbon coated aluminum, because in order to avoid the resistance between the electrode and current collector. So in order to avoid that, carbon coated aluminum will help. You can adjust very nicely with our material in the carbon coated aluminum file. Then we can get the very nice results. This is very important. You need to control all the parameters. Then only we can increase the specific capacitance. If we see the operating voltage, cell configurations, and electrolyte material, as I said, electrolyte is very important to determine the final voltage of the device. And if we see the resistance, RES, that's why equivalent series resistance, or is a resistance, equivalent series resistance. It depends on the how much active material loaded and the package of the cell, current collector, and also the how much during time and additives. These and all creating the resistance. As I said, IR drop, this internal resistance is equal to ESR and EDR. This is contributed, we called IR resistance. Then from this and all you can calculate by the impedance actually. If you see the specific capacitance calculated by the CCD, that is called CB and CD, and Nichols plot, if we can calculate the impedance as well as the your performance there. So if you see the operating voltage, maximum energy density, maximum power density, usable energy density and usable power density, and that is finally go for the cell performance. So time constant, cycle stability, it means you can have cells should have the very long cycle. So these all are this complex matrix. We need to consider every point for the fabrication of the cell in the commercial level to compare the maximum. So these are the very important for the people are who's working in the device level, in the cell level also, they should consider, because if you go for the very, they need to, most of the people, they're giving very less current. For example, 1 ampere or 0.5 ampere per gram, they'll be tested. They're telling the cell is working well. If you go for a very high current, then you can reality, the reality of the material. Then what are the resistances creating? What are the real performance of the material in real time analysis? We come to know that. So then, if you see the commercial point of view, the fabrication, everything is very important, because specific capacitance is very important. Electrical conductivity, because your material should be, when you are prepare the material, we are adding activated carbon, that is the active material, and we need to add some conductive additives, for example, carbon black or binders. So these three mixers uniformly mix together and make the slurry, and we are putting the current collector, then only we can get the very nice electrical conductivity. If there is no electrical conductivity, your rate capability will affect. So that is very important parameters for us. Then cycle stability. Cycle stability depends on the several parameters. As I said, it should be resistance-free cell. Then only you can go for very good high performance material, and the pores and the ionic size should be matched. Then only you can get the very long cyclability. And mechanical rubber, because some people are working in the flexible electrodes, because it's having the mechanical rubber, and also some people are working on the coating electrode, that is having the very good adjustment property with the electrode and current collector. So even it's not peeling out from the current, that is very important. And of course the fabrication cells. These are all are the very important for the supercapacitor performance in the commercial level test. So now that's Srinivas.
Yes, sir.
So may stop now, then we can continue on.
Sure, sir. Sure.
Then I will talk about indigenous material design and what are the prototype level and application of supercapacitor. I will cover on afternoon.
Sure, sir. Sure. So shall we
now
take the questions
what
from
are
the
questions
participants?
Coming now?
Yes, we will. Yes, sir. So first question we have is from Dr. Karthikeyan. In what way supercapacitor is superior than lithium-ion batteries?
Supercapacitor is superior to lithium-ion batteries, as I explained. Supercapacitors having the high power density. Lithium-ion batteries having high energy density. So power and energy, some applications we need high power. Then wherever the power demand, then supercapacitor is suitable candidate. Then lithium-ion batteries high energy density. So wherever the energy is required, then energy density lithium-ion battery we can use. But nowadays we need both. For example, EV applications and all, we need both power and then hybrid systems is coming now. I think lithium-ion batteries and supercapacitor are going to be hybrid, good combination in future.
Yes, sir. And we have one question from Al Saheba. The discharge rate of supercapacitor is very high. Then why supercapacitor?
Okay, discharge rate very high. That's the advantage of supercapacitor. Discharge is very high, means it's very high, deliver the high power. So, for example, supercapacitor can be used as the engine startup. So, when you are doing the engine startup, when you are starting the engine, we need very high demand that time. So it will take mostly from battery. So if you take the more current from battery, you can abuse the battery lifetime. Suppose if you put the supercapacitor in there, it will release the high power during the start of the engine. Then when the vehicle is moving, then the supercapacitor itself charging by the from your engine, then you are charging by the engine is having the everyone the attractor. From that you can charge by the supercapacitor. And also advantage of supercapacitor is how it's releasing energy fast. The same time it absorbs the energy fast. So regenerative braking, whenever this is another concept supercapacitor very useful. Regenerative braking, whenever you have regenerating applying the brake and the accelerator, when applying the brake, then your kinetic energy convert electrical, that is can be stored in supercapacitor. That is an upcoming cars and that they're going to implement in supercapacitor. So this kind of applications, wherever the power delivery is needed, then supercapacitor is beneficial, even though it's having very low energy density.
Yeah. Continuation to that, I think she's asking, sir, can you please repeat the meaning of ESR and EDR?
Okay, ESR means that is a equivalent series resistance. It's the equivalent series resistance is a series resistance between the current collector, whatever the carbon quarter on the current collector, or it also having some and also current receivers. These are all resistance created. That is the ESR. EDI, the equivalent diffuse resistance. That is from the your Necospla. You can easily see that from the Necospla. You can see that semicircle is coming. It means you can establish this from contact resistance or the ion diffusion resistance, because ion can diffuse into the electrolytes, that also giving resistance. That is called equivalent distribute resistance.
Right, sir. So Dr. Lakshmipati B, I think he has a remark to make there. So in slide number 44, it is mentioned as kg power -4 and another one termed as kg power -1. How unit will vary, sir?
Where? I don't know. Where?
In slide number 44, he is suggesting.
44.
Yes, sir. So he says that
So whatever per kilogram.
Yeah. So he says kg power -4.
Yeah.
He saw somewhere.
Not -4, -1.
Yeah, it's mine. Yeah, I think he saw somewhere.
Whatever per kilogram unit.
That's right, sir.
Actually, the energy density is calculated by whatever per kilogram. Power density is calculated by watt per kilogram.
So, Mr. Prabhakar Patil has a question. So, which synthesis method is suitable for increasing the porosity and surface area in fabrication of electrodes using metal oxides?
Or the metal oxides.
Right.
Metal oxides, anyway, I'm talking about here, activation procedure. It depends on the, physical. Metal oxide, there is a lot of phenomena, maybe, solid mixture or some salt gel methods, or pseudocapacitor. There is a lot of methods available, hydrothermal synthesis. So, a lot of methods available for the metal oxides for pseudocapacitor applications. But carbon, I'm talking about industrial scale. The physical activation is very cost-effective technology compared than the chemical activation.
So we have one more question from Mr. Askar Ali P. Electricity is needed to charge EV, and major part of electricity is produced from thermal power plants in India. So how EV reduce CO2 emissions?
Yeah, good question. Anyway, EV is now, I think, charges by electricity. But as I said, no, we can put the solar panel. We can charge the solar panel, a renewable energy. We can charge the EV. So renewable energy now, solar panel is booming a lot. Now we are talking about gigawatt or capacity. Compared than the last 15 years before, solar panel is very less interest in India. But now everywhere you can see even Cochin airport completely run by solar panel. Not partially. They're taking for 5 hours, 6 hours run by complete airport by solar panel. So solar panel, we can have all the wherever the sets are available, we can implement, we can charge. But what is the problem? Fast charging the solar panel is questionable, but the technology will come, then we can charge by solar panel.
So we have one more question from Mr. Deepak Kumar. Sir, as you mentioned about the importance of current collector in reducing ESR, so which current collector you think is best for investigating supercapacitors?
Yeah, generally people are using aluminum foil, commercial level aluminum foil. The aluminum foil, pure aluminum foil, what is the problem? That coating in aluminum foil with your material is not this giving some interface. That's the problem, because aluminum also is giving some very fine layer of aluminum oxide, because aluminum is highly air oxidation. So in order to avoid that, and also because your particle size more, when you are coating very bare aluminum foil, your adjustment is not very proper. Then you need to put some carbon coated, very thin. Now our commercially available carbon coated aluminum foil. When you carbon coated aluminum foil, then if you coat your material, you can have the very good. You can reduce the ESR.
Sir, so we have one more question from Kritika Balasubramanian. So, sir, e-vehicle leads to increasing e-waste.
Sorry, e-vehicle.
E-vehicle leads to increasing e-waste.
E-waste.
Yes, sir.
Yeah, but anyway, always everything there is some, something e-waste is coming, then recycle of e-waste, then other research we need to do. Then it's always a cycle.
Right, sir.
So every technology having the whatever you're asking, yeah, that is correct. For example, it's not possible to completely get rid of IC engines tomorrow. Not possible. Every technology is coming their own growth rate. So if you coming like, for example, electricity, now 100% we are depending on electricity. Suppose suddenly electricity, now population is increasing. So we say, for example, pollution control. We can not only developing the EV vehicle to control the pollution, not required. When increasing the vehicles, can you see 20 years before, how many vehicles are there? Pollution control. So that's why we need to reduce this. Then there is technology is coming. We can suppress somehow, not completely. So these are the same thing that I am correlate this questions also. The e-waste, of course, there is something that let see so many people criticizing, also appreciating, because power plant definitely generating a lot of CO2. Then your EV vehicle, you are telling reduce the CO2. So this is a very difficult question. This is difficult to answer this question, because of course we can suppress somehow. No, suppose if you use the consumption of petrol or whatever that is electricity by electrical grid, by using renewable energy, some percentage is decreased. So today some percentage, tomorrow that percentage is going to be in some sector increase. That's the reason research R&D is having own growth rate. See, lithium-ion batteries developed very long back, but how long we are using lithium-ion battery? Even our everyone research has patient. Our good enough, he received the Nobel Prize in age of 98. So he is one of the oldest person received the Nobel Prize in the year of 98. You see how patient he is waiting the technology really to the commercialization. So every technology having the own rate of growth. So we should allow them. Then we need to enjoy the fruit in maybe future generation. We are enjoying or not, but at least our future generation will enjoy, right?
Yes, sir. So, Dr. Lakshmipati has, I think, the same person who has asked about the slide 44. So he's asking whether it is color of blue indicates 1 kilowatt per kg, followed by green color 5 kilowatt per kg. Is it correct, sir? The same slide what we are seeing now, sir. The same slide we are seeing now. So he just wants to make sure that blue is
anyway, this is actually it's not my slide. This is some of the people reported in review article. I just put in that just for the, but actually this is just for the comparison. What I'm point out here, different material having different type of whatever program, and if you change the material and properties, generally what was our main idea is energy density, power density. This is very important for the commercialization application. So that's why we need tuning our properties. That is the intention.
Yes, sir. So one continuation question, maybe the last question, I think.
Yeah.
So my question was, self-discharging rate of supercapacitor is very high and it gets discharged quickly. Then why supercapacitor? I think
self-discharge, that is a very common question. Everywhere people are asking. I don't know how many people they really see the self-discharge of Maxwell, because we purchase the Maxwell, we are analyzing the self-discharge of Maxwell. If you charge this one, it will withstand the charging. For example, 2.7 volt Maxwell is releasing 3,400 farads. This is the highest farads in Maxwell. That is why I am going to maybe next afternoon I am going to discuss that. If you want charge 2.7 volt, then after 1.5 months, it's reduced to 2.5. I don't know how many people knows this. So commercial level, self-discharge is common factor for the people are discussing in the lab level. Lab level self-discharge is depends on how your device making, electrolyte injection, concentration. There is a lot of technical issues are there. But self-discharge of not bad, that much battery. It's coming in several months. We practically observe in our lab.
Yes, sir. So I think that's it from the Q&A, sir. So we'll take a lunch break now for 1 hour.
Yeah.
And at 2 o'clock we will meet again, sir.
Yeah.
Thank you for your time and
Thank you very much.
Efficient
My
delivery
pleasure
of the
to share.
lectures. Thank you.
Thank you.
So all the attendees, we will meet at 2.